Hello and welcome to another video. I'm doing a couple today, and I'm going to try and do the specimens from the mat. I like this question because firstly it's about binomial expansion. Secondly, I think you can do it with just AS maths knowledge. Thirdly, it is very difficult though, and you know, I like people to understand that step 2 questions, they are the toughest if you ask me. I think they're harder than step 3. They're really tough, but it's not tough because of the content. The content is literally just binomial expansions where n is a positive integer, yeah? And so this is, you know, really reliant on just binomial expansions from AS maths. Now you can see though in the examiner's report, and it's always well worth looking at the examiner's reports, which are freely available for STEP. You know, they'll tell you exactly what the easiest question in the paper was and what the toughest question in the paper was according to how people found it. Well, this was the least popular and also the one with the lowest average score, so people did not like this, whether they had a go at it or not. And then it says a few more things. We'll get into what else it says here, because I made a mistake at the end which they picked up on. It's like, yeah, I would have messed it up and lost the marks there. It's always important to be frank and honest, but let's talk about how we can try and get full marks now. Now, it's one of those questions which is difficult really because it relies a lot on a really solid understanding of algebra, but also when they denote new kind of like functions, if you like, then you know that can be hard to follow as well. Anyway, let's have a go at it. For positive integers n, a and b, the integer cr, where r is between 0 and n, is defined to be the coefficient of x to the power of r. In other words, c subscript r is just the coefficient of x to the r, yeah? In the expansion of a plus bx to the n. Write down an expression for cr in terms of rn, a and b. Now that is really not too bad. Always annoys me actually instead. They never put, like, they put part 1, part 2. So what is this, part 0? Right, it's kind of annoying. But I'm going to call it just, well, let's just start here. Okay, so if I'm expanding a plus bx to the n, yeah, then each term can be found by, okay, and this is fairly obvious. Now remember, we only care about the coefficient. Now we're going to have, if we're doing CR, where R is basically the power on X, yeah, you're going to have A to the power, well, you're going to do N choose R. Should we start with N choose R? Because you always do N choose R in these expansions, yeah? Like, and then you're going to be doing A to the power of, well, let's think about A second, B, well, let me write it down as bx, yeah? But I'm going to scribble out the x in a second, yeah? I want x to the r to be, involved because I'm considering the coefficient of x to the r, but I'm only considering the coefficient of x to the r, and so I'll get rid of the x, and it's just going to be b to the power of r. Now, what is a going to be to the power of? Well, n minus r, yeah? I think that's fairly easy to just write down straight away. I hope you agree with me on that. Essentially, maybe I should have explained it a slightly different way. We've got c subscript r times by x to the power of r. That's what we're thinking about, the coefficient of x to the r. And that's why the x to the r on this side I've just cancelled, because I have an x to the r on that side. Okay, so that's going to be the general term. I hope that isn't too bad either. What did they ask for next? Okay, for a given n, a and b, let m denote a value of r for which cr is greatest. In other words, if you expanded these brackets, you're going to have an x to the 0, x to the 1, x to the 2, all the way up to x to the m, maybe it's like 7, all the way up to x to the 7. We're looking for the biggest coefficient, because m denotes the value of r for which cr is greatest. So, sorry, we're looking for the position of the greatest coefficient. So you want CR to be greatest, so maybe like there's a 108x cubed in there, and that's bigger than all the other coefficients. Well, like then wherever that is, that position, because R denotes the position in the expansion, it denotes the power on X, yeah? So basically M denotes the power on X for which has the greatest coefficient, yeah? I hope that makes sense. That is, Cm is greater than or equal to Cr for 0 up to n. So you can see what's difficult about this question. It's not actually the maths answering it, it's understanding what the question is asking, yeah? Now, my immediate thought on this was, as the coefficients go up, what tends to happen when you expand brackets, yeah, when this is a plus, yeah, forget the situation when there's any negatives involved. but if this is a plus, if you've ever looked at the coefficients, they tend to go up and reach a peak, and sometimes there's two of them which are the same value, like 216, 216, something like that, and then they tend to go down. Yeah, so we're looking for whereabouts the position is where you get the greatest value. Yeah, but the fact that they go up then they go down made me think, well, I need to take like to the left hand side and the right hand side of CM here, because M denotes the value of R for which CI is greatest. Yeah, so my thinking was, well, as CM is always going to be greater than or equal to CR for all R, yeah, where 0 is less than or equal to R is less than or equal to N, yeah, they told me that, remember, I can use that, they told me that, then I can certainly argue that CM should be greater than or equal to CM plus 1. Basically, I was thinking, oh, it must be like, you know, I need to show that this term is going to be greater than the term ahead of it, and then greater than or equal to the term behind it. And so that's what I was thinking. Now, I can now use my formula up here. The left-hand side is going to be n choose m, multiplied by a to the power of n minus m, multiplied by b to the power of m, because r is just being replaced with m there. On the right-hand side, you've got n choose m plus 1. Times by a to the power of n minus n plus 1 times by b to the power of n plus 1. Yeah. Now straight away I looked at this and thought, this is crying out to be simplified. Yeah. Firstly, I'm gonna put the b's together. Let me just clear that up. I'm gonna put b to the n plus 1, b to the m here. Let's just leave a b on this side. Same with a. This is a to the n minus m. This is a to the n minus an extra one. So this is bigger than this one. You know, think of m as 5 and m as think of like n as 8 and m as 5. That would be a cubed, and this would be 8 minus 6. So that would be a squared. So in other words, over here, if you do that divided by that, check it, but I think you're going to get an a there. Yeah. When you do m minus n minus m plus 1, you're left with just 1. Okay, so we've dealt with all the a's and b's now on both sides of this inequality. On this side, we're just going to have m factorial over m factorial n minus m factorial. Let's make it a bit closer now. I just want to make it nice and clear. And on the right hand side, you're going to have something a bit more complicated, because you're going to have m plus 1 factorial on the bottom, and then n minus m plus 1 close brackets factorial times by b. Yeah? Okay, what cancels here? The n factorials for a start. And then think of it like this. If you times m plus 1 factorial over here, you're going to have m plus 1 factorial over m factorial, which is just m plus 1. And I'm going to times this onto this side, yeah? Oh, I hope you're happy with me just saying n plus 1 factorial. In general, 7 factorial over 6 factorial, that's obviously 7. 9 factorial over 8 factorial, that's obviously 9 for the way factorials work. I hope you can be convinced of that. And in general, m plus 1 factorial over m factorial is just m plus 1. Yeah. So that's the idea I'm using there. Okay, same on the right hand side. Let's just have a look at it. What have we got? We've got n minus m factorial over n minus an extra one. If you're taking away an extra one, you're just going to leave n minus m on the top times by b. Check you're with me on that. Try plugging in numbers, you'll see what I mean. You know, if m was 8 and m was 5, this would be 5 factorial sitting on the top, but this would be 8 minus, what did I say? N is 8, m is 5, so we would have 8 minus 6, which is 2, you know, and here we've got 8 minus 5, which is 3, so we'd have 3 factorial over 2 factorial, which is just 3. So you're going to be left with the n minus m there on the top. Okay, so now we can just rearrange this into the way they want the answer. Now I think they had, if you look at what we're heading towards, what we're hoping to get, we're hoping to get this. I'm hoping to get one side of the inequality or the other. So I'm going to make m the subject. Yeah, and to make m the subject, standard stuff, put it all on one side, am plus bm. Let me make it clear that it's an m because there's n's involved. So, and then I'll have nb minus a, I think there. And what does this give me? Now, bear in mind I need to factorize this and then subtract. I'm going to have m is greater than or equal to n times by b minus a over a plus b. Now, that doesn't quite look like either of them at the moment, but it looks more like this one than this one. So I'm going to try and fiddle with it so I turn it into that one. So I just wanted, what do I want on the top? I want an bn plus b, yeah? And at the moment I've got bn minus, oh hang on, why have I factorised that? There's a little mistake there, mistakes creep in. So it's just going to be nb minus a. But as I say, I want on the top an nb plus a b, yeah? So let's make that nb plus b. And then I'm going to have to take away an a and take away a b over a plus b, yeah? And that's the same as obviously minus a plus b, and then I've got the answer. I'm going to have b times n plus 1, I'll factorise that a little bit now, over a plus b, minus, because that's the same as minus a plus b, you've got minus 1 there, and you've got it, yeah? Okay, so that really made me happy. Once I saw that, I thought, oh, I've done that. And actually, this is one of those interesting questions where this bit's harder than parts 1 and 2 here. It's easy to use this result for parts 1 and 2. And I don't think 3 and 4 are that bad if you're happy with graph sketching, but there we go. Okay, so that's half of it proved. I've proved the first bit, the left-hand side of the inequality. I'm sure you realise straight away that I'm going to say Cm should also be greater than or equal to Cm minus 1 now. Like I say, the reason I can do this is because they told me that Cm is greater than or equal to Cr for any r. Yeah, it's supposed to be the biggest term, the biggest coefficient in the sequence of coefficients in that expansion. So same approach. M factorial over m factorial n minus m factorial multiplied by just remind ourselves a to the power of n minus m and b to the power of m. That should be greater than or equal to m factorial over m minus 1 factorial n minus m minus 1 factorial multiplied by a to the n minus m minus 1 multiplied by b to the power of m minus 1. Okay, that's clearly smaller than that one, so the b is going to end up on this side. Just same as before, you're just going to have an a on this side. And that's because if you do that minus that, you end up with n minus m plus 1 minus m plus m, yeah, and you end up with a to the power of 1. And so what have we got here? We're going to also cancel these. I'm doing this one slightly quicker. That m is going to go over that m factorial is going to go over m minus 1 factorial, leaving an m on the side here. And this is going to go over here, leaving an n minus, oh sorry, that's going to go onto that side. That's going to go, yeah, no, that's going to go on that side. This is going to go over here, I think, because if you've got n minus m plus 1, after you take out the brackets, over n minus m, obviously that's one more than that one. And so on this side I've got n minus m plus 1 times by b equals ma. Once again, just make m the subject, so nb plus b is greater than or equal to m plus m, oh sorry, mb plus ma, and then just factorise, and you can write the answer down. And so, combining these two inequalities, we derive the result. There's our two inequalities. M's bigger than that one, but M's smaller than that one. And so we can say, hence, M is trapped between basically a number minus 1 and the number itself. Cool, we've proved that. Now we do need to justify the next little sentence here. They said deduce that m is either a unique integer or one of two consecutive integers. Now as soon as I looked at this result, I thought, well, that's clearly true. And I wonder what they actually want me to write down to demonstrate it, because it's just an immediate deduction you can see from this. Because the way I put it, the way I explained it in the solution I just wrote up was I said, now let Q equal b to the n plus 1 over a plus b, just to make it slightly easier to see what's going on. We've got m is definitely trapped between q minus 1 and q, but the thing is, q, unlike every other thing in this question, q is not necessarily an integer. It really isn't, yeah? Now, if q is not an integer, bear in mind m must be an integer. No, m is definitely a member of the natural numbers or positive integers, yeah? Then m has one unique value. Because you're essentially saying, let's say q was like 4.5, then m would be between 3.5 and 4.5, so m would have to be 4, because m is an natural number, an integer, positive integer, yeah? But on the other hand, if q is an integer, then m could take two different values. And what that's saying there is there's two values which are the same next to each other in your binomial expansion. If q is an integer, then m has two possible values. Yeah, and cm could basically is either one of them. Gm takes the same value for both. Now, let GNAB denote the unique value of m, if there is one, or the larger of the two possible values of m, and this is where this subtle case comes into play. Yeah, so if you've got m stuck between 5 and 6, that GNAB is going to make m be the bigger value, 6. So it's almost like this part of the inequality matters more now, if you like. Okay, so there we go. Right, now we actually get into part 1, part 2, part 3 and part 4. I honestly think that's the toughest bit in this question. That was the bit I found toughest anyway. Okay, part 1, you could do this, and this is the point, right? With STEP and MAT, don't think that if you can't do part 1, you definitely can't do part 2 or 3. That's not true. That's why it's a show that you can pick up marks. I mean, admittedly, they give you way more credit for full answers, but, you know, they do mark all 6 of the questions in this, and it's worth getting every mark you can. So if if this looks like the easiest mark to get, then let's do it. Okay, remember GNAB is just m, yeah? So let's just try plugging it into here, those values of n, a, and b, into our inequality. Yeah, because m is kind of like, it's not exactly the same as GNAB, but it's the bigger value where there's ambiguity on what m should be. It basically is the same thing, but you're going to round up if there's two possible answers. Okay, so let's just plug those in. What have we got? 3 times by 10 over 4 minus 1 is less than or equal to m, which is less than or equal to 3 times 10 over 4, and that's telling me 6.5 and 7.5, and as m is an integer, there's a unique value here, and m equals 7. In other words, G913 equals 7. Okay, for G923, it's obvious that this is going to be the case where there's two different values and you'll need to take the larger one. It's just the kind of thing they would do. Okay, we're going to have 3 times by 10 over 5 this time, minus 1. 3 times 10 over 5. And you can see here we're going to get 5 is less than or equal to m, which is less than or equal to 6. But when you're using the G notation, you take the bigger value, and so this is going to be equal to 6. Done. Part 2 is not really any more difficult, yeah, 2k a and a and 2k minus 1 a and a. And it's weird actually in this question, often in step questions, like, they really link up, but I would almost treat each one of these as just a different question. Okay, G2k a a, I'm just going to use the formula again, really am. So we know that m here is stuck between, what do we get here? We've got a times by 2k plus 1 over, and I'm just plugging numbers in, 2a, oh, let's not forget the minus 1 on this side, and then this will be exactly the same because just the same without the minus 1. Just cancel. Yeah, that's 2k plus 1 over 2 minus 1. Well, should we make that 2k minus 1 over 2? Note, remember as well that they define k to be an integer here, so this is definitely not an integer, so m is definitely unique here. Yeah, a's cancel again, and we're going to end up with 2k plus 1 over 2. Yeah, well, you know, this is going to be k plus a half, and k is supposed to be an integer, and therefore m equals k, and therefore g2kaa equals k. So really not difficult that, and you know, the next bit's the same, 2k minus 1 aa, it's not difficult. Okay, right, we're just considering that. Let's just draw a line under that one to show you working nice and clear. Okay, so this time we're going to have a times by 2k over 2a minus 1, and then a times 2k over 2a, and there we go. Now we just cancel it. So what have we got here? Just k minus 1 up to k. Remember, k is an integer, take the bigger one, and so g 2k minus 1 aa is k once again. Same answer as before. Done. That's part 2. I'm sorry I've gone through part 1 and part 2 quite quickly, but honestly I would have thought that they'd be way easier than proving this result just by plugging the values in. Yeah, we've found them both in terms of k. Right, part 3 and part 4 get a bit tougher. Let's drag this across. Scroll out a bit. Sorry, just giving myself a bit more space. The difficult thing with step 2 questions as well is obviously doing it in time conditions, neatly, clearly, so the examiner can understand you're working. Now, you know, they tell you in the mark scheme so many times, like, why wasn't there clear diagrams drawn by students? It's what they always criticise students for, and I will too. You know, like, drawing a graph is the easiest way of doing these kinds of questions. Okay, for fixed n and b, that just means n and b are constant, and anything which isn't fixed is a variable. Yeah. Now we already know that m is always less than or equal to, I think it was b times m plus 1 over a plus b. Yeah, and we're dealing with a general case here, and we're trying to make GNAB as big as possible. Yeah, and remember, GNAB is basically m here, because I've taken the end of the inequality because I need the upper bound. Yeah, and so I'm just going to think, well, n and b are fixed, they're fixed. That means a is varying as m varies. Well, let's draw a familiar graph. Consider y equals b over m plus 1, remember they're just constant though, they're just numbers, over x plus b. They're just constants, the b and n are constants, the y and x are the variables here. We can draw a graph of that, not a problem at all. And actually we only care about the case where x is positive, because x is representing a here, and a is a positive integer. But let's just draw the whole thing, because it's not that difficult to draw. Okay, it's got a vertical asymptote at x equals minus b. And otherwise it just looks like your standard, you know, reciprocal curve. It's a reciprocal curve moved to the left b units, if you like. Now when x is 0, it's going to go through m plus 1. And remember, we're looking for the greatest value of m here, where, well, m is kind of like your y, but remember though, n has to be a positive integer and a has to be a positive integer here as well, because initially I thought, okay, so a is going to equal 0 here to maximise this, like it will maximise the y, which represents the m, and that will give me a maximum value of n plus 1. That is wrong, and they're mocking me for it in the here, look, because this is a mistake I made. I did the whole thing. I got part 4 right, but I got part 3 wrong. In the final 2 parts question, some candidates mistakenly chose the value 0 when asked for a positive integer. That was me. I didn't look. I didn't remind myself that a is a positive integer. Yeah, it's one of those things you hope you'd catch when you check through your working at the end. So a equals 0 isn't good enough. Yeah. Actually, we need it to be a positive integer. And the biggest value of that is going to occur when a equals 1. Yeah, and we can just see that because that's a decreasing function. So we want it to be as, you know, as high up as possible, and therefore a equals 1 will generate the greatest value of y. will generate the greatest value of y whilst x is a positive integer. And it's just because of this restriction of positive integers, natural number positive integer, yeah, so a equals 1 will maximize GNAB. Now, I wouldn't normally have time to do this in the exam, but I do want to just encourage you to think, does my answer make sense at the end? Yeah, and it does, yeah. Basically, if you're maximizing GNAB, you're maximizing where the largest value happens in your expansion, yeah? And that should happen, in other words, you're hoping it will expand as late as possible. The biggest coefficient, if you like, in the expansion will arise as late as possible if you're working with descending powers of x, yeah? It will arise on the highest power of x, if you like. Well, that obviously happens when this is 1 rather than 2. Let's say you've just got 1 plus 3x to the power of 4, yeah? And then consider like a 2 plus 3x to the power of 4, yeah? We're basically saying you want this to be a small number for this to occur as late as possible. And of course, yeah, that works. And by the way, when a is 1, we can now plug a is 1 into this. We can see exactly what this will be. And furthermore, and the question didn't ask for this, but I'm just going to point out, GNAB should be less than or equal to, well, with this with a equals 1 plugged in, so you can have bm plus 1 over b plus 1, yeah? Now let's just see if it works in these cases. Well, expanding this out doesn't take very long. We've got 1 plus 4 times 3x plus 6 times 3x squared plus 4 times 3x cubed. And I'm just going to show you that my answer makes sense, plus 1. And so that gives you 1 plus 12x plus, what's that, 9 6s 54x squared, and then 27 times 4, 108x cubed, plus 1. Now, we're saying basically that term with largest coefficient, which is a 0, 1, 2, third term along, yeah? Now, when you plug in, sure enough, b equals 3, which is what I've got here, n equals 4. What have we got there? 3 times by 5, which is 15, over 4, which is 3.75, yeah? Well, we're saying this is less than or equal to 3.75. In other words, it's 3, it's the third term. See, it's worked. It's actually worked. So the third term is going to be, starting on 0, it's going to be the biggest coefficient. And you're not going to get a bigger coefficient, like your coefficient's going to occur earlier on in the list when you do 2 plus 3x to the power 4. Because suddenly you've got 2's to the power of things, haven't you? Like, etc, etc. And I'll just leave that, leave you to think about that. But yeah, my answer makes sense. That's what I wanted to point out. Okay, for part 4, I used exactly the same technique. I'm just going to draw a graph. For fixed n this time, greatest possible value of gn1b, and for which values of b is this greatest value achieved? Values of b suggests there's more than 1. Okay, so gn1b, we know that m is less than or equal to n times by, or b times by n plus 1 over a plus b, which is 1 plus b, yeah? N is fixed, so once again m and b, though this time, sorry, are my variables. So consider the graph of y equals x times by n plus 1 over x plus 1. Now, you might not be happy with drawing a graph of x over x plus 1. There's lots of ways of thinking about it. Get good at graph sketching. It really helps. I like to do it like this, actually. I like to think, well, I'd like to eliminate that x plus 1 on the bottom. Essentially, I'm doing long division here, so I need a multiple of x plus 1. Well, how about n plus 1 times x plus n plus 1? Because I could obviously factorize out n plus 1 to leave n plus 1 times x plus 1. And then I'm going to take away the n plus 1. This just means I can straight away draw this, and this comes from lots of experience with graph sketching. Now, what does this graph look like? Well, it's really similar to if you had like a k minus c over x plus 1. It's basically like that, and that's what I thought. So I could draw it now. I thought I can definitely draw that. It's going to be kind of an upside down reciprocal graph because it's been reflected and it's been moved up a bit. It's going to have an asymptotal Wales k, but our k is n plus 1. And it's going to go through 0, 0 actually as well, because when x is 0, you have n plus 1 minus n plus 1. And so it's going to go through 0, 0, and it's also going to have an asymptote at x equals minus 1. We don't actually care about the left-hand side because x is strictly positive here. It's going to be doing that. Yeah? Like that. Another solution I saw online for this question actually differentiated. It's like there's no need to differentiate here. We've just got to remember now that m is definitely an integer. Remember that y represents m on this graph, and this never gets to m plus 1. So I guess the greatest value is, you know, g n1b equals n. Yeah, it must be under the n plus 1. Remember, n plus 1, it never actually reaches that, so it must be n, and n is an integer, and gn1b must be an integer. Yeah. Now, where does this achieve this greatest value? For what values of b? Well, let's just use the formula. Yeah. Remember that this kind of represents your m, and so n is less than or equal to n plus 1 times by b over 1 plus b. Let's just rearrange this to find the restriction on b. They cancel, and you get b is greater than or equal to n. Finished. And that's that question. Now, I know it's quite abstract. I'm going to rate that about an 8 out of 10 in terms of difficulty on my casual kind of rating scheme. But I'm going to, certainly if there's any super bright A-level mathematicians, after we've done binomial expansions, after I've shown them an easier step or math question on binomial expansions, I'll show them this one if they're feeling too confident, because it's difficult, that very hard to get full marks, I think. Like I say, I would have clowned up the, suggesting that A could be 0 here, but there we go. Hope it was useful, and well done. Keep up the hard work. Bye bye.